So welcome back, everybody, to EE240. So as I mentioned last time, I'm going to be gone on Thursday, so we're going to be taping ahead the lecture for that later tonight. So that's going to be 5:30 to 7 p.m., just in 293 Corey here downstairs. So hopefully if any of you guys can make it, please do. Otherwise, I'll just be sort of randomly babbling to the walls, and that won't be particularly good for any of us. So as I said, if you can make it, please do come by. Just maybe to just sort of do a quick poll, how many of you guys who are here can make it to the tape ahead? And are planning to make it to the tape ahead? Okay, very good. Thank you. All right. So other than that, as you guys know very well, the project phase 3 is out. And hopefully if people have at least started looking at that, I realize some people have other projects that they're perhaps more frantically busy working on at the moment. But please do make sure you go ahead and get started, at least if nothing else, getting an idea of what we're asking you to actually do. Because indeed it will take you some time, and so you make sure you've budgeted enough to really get going on that. You should actually know basically everything you need to know to really sort of do the complete project. If not by the end of lecture today, then basically by the end of the tape ahead lecture later tonight. So please do, as I said, make sure you go ahead and get going on that. So before I sort of dive back in, any questions on either project or class material or anything like that? Just out of curiosity, how many of you guys have actually looked at phase 3? Okay, sounds good. All right, so unless there's any questions, let's go ahead and sort of finish up where we were last time, which, if you guys remember, we spent a lot of time talking about matching. And I think we basically covered almost everything I wanted to there. There was just one last piece of it, which is we kept saying that in all of these matching equations there was that distance term, and we were going to try and do everything we could to keep that distance term to essentially be 0. So the only thing I really wanted to show you is how we're really going to make that happen. And in fact, what essentially is a common layout technique to not even get rid of that, but to get rid of certain systematic types of offsets. And in particular, these sort of so-called linear gradients. So let me just sort of show you how you might do something like that. So let's say you have, as an example, 2 transistors that you'd like to have matched to each other. So let's just call those things, let's say, A and B. Okay? So hopefully this is clear from this picture. These two obviously have some distance from each other. And of course, if there's some kind of, let's say, linear gradient in the process. So as an example, let's say that everything that's on the right-hand side has slightly thicker oxide than everything that's on the left-hand side. Then of course, in the picture that I've drawn here, things won't be very good, because that B transistor will on average have higher, rather thicker oxides than the A transistor would have. Okay? So just to make sure that that's absolutely clear, as you can imagine, when we really build these things, you'll typically build them out of unit cells. And hopefully you paid sort of close attention. You'll used to have sort of a couple of transistors inside of there so that the current flows in both directions. So what I'm going to do is just sort of split each of these transistors into a couple of pieces. So for example, I have the A on the left and the B on the right. And again, I'm just splitting them into 2 halves to make sure that it's clear. So it turns out that the sort of trick to both getting rid of this gradient and realizing how you would sort of make the effective distance be 0 is to realize that when you say what the sort of distance is, what you typically mean, let's say from a mathematical standpoint, is you're looking at the distance from sort of the center of mass or the centroid of each of these transistors to each other. So as an example, when I did the split, hopefully it should be very clear. In fact, it might have been clear before. The distance between the 2 centers is really this. Okay? So the whole trick to basically getting rid of these effects is to do what's called a common centroid layout. In other words, we're going to take these sort of individual pieces of transistors that I drew here and kind of rearrange them so that the center of each transistor is basically the same as the center of the other transistor as well. Now, in case you don't believe me that this is possible, let me just sort of draw one simple example of how you do that. And hopefully it'll be clear why indeed it actually works. So just as an example, let's say I did my layout something like this. Okay? So clearly the center of the A transistor is indeed right there. And of course, the center of the B transistor is also in that same spot. Okay? So notice by doing this, even if I have any sort of linear gradient in any which direction, so let's say from right to left, diagonally like this, top to bottom, etc., all of them, because I've made the centroids of those 2 transistors sit in the same spot, should actually affect both of those transistors in exactly the same way. Okay? So this technique is a good one to know about, simply because if you really want to do very, very high precision matching kind of stuff, this is indeed the sort of types of techniques you end up having to play with. Now, having said that, particularly in modern technologies, if your transistors aren't really, really big, or you don't have a really big array of devices, turns out you don't necessarily have to play exactly this kind of trick. Simply because if everything you're talking about is sufficiently small, then basically the linear gradients don't matter all that much. Because, if, as an example, you have something that's only, 2-3 microns on the side, right? If your chip is, let's say, 10, 15, 20 millimeters on the side, and, 2-3 microns is actually big enough to see a substantial gradient, then basically you'd be screwed anyways, okay? So the point here is that, common centroid is indeed a very good technique. It's something you should know about, especially if you want to be sort of dealing with fairly large arrays of devices. But, don't go sort of super overboard with it, because as you can probably imagine, it's kind of a pain in the butt to actually do this for anything more complicated than kind of a couple of devices, right? You can very quickly come up with some very, very complex patterns that might actually be a major pain in the ass to actually wire them all up, okay? So again, this is an important thing to know about, and if you sort of take a look at that Art of Analog Layout book, they'll give you a bunch of sort of examples of what these common centroid things look like. But, don't just sort of start doing this just for the sake of it, because it can indeed be a bit of a pain. Okay? Yes.
Sort of a sizing rule of thumb for when you want to start doing this?
Okay. So it's a good question. The question was, is there sort of a sizing rule of thumb for when you want to start doing this? It's kind of also tied to, let's say, how precise of a matching you really need, right? So if you really need something like, let's say, 10, 12, 13 plus kind of bits of matching, then that's where you really probably want to start playing these kind of tricks, okay? But if you're talking about maybe something like, 6 to 8 bits or so, and also perhaps more importantly, where your structures just physically aren't that big, meaning that you're only talking about maybe 10, 15, 20 microns for the whole thing to begin with, maybe even 50 microns, then probably the linear gradients just don't matter that much, because the whole structure's small, and again, if you had a big linear gradient in that space, your chip would kind of be dead anyways. Does that make sense? Or it's a good question. Okay. Any other questions on this? Or how many of you guys have seen common centroid before? Okay, good. All right. So unless there's more questions on this is basically all I really wanted to say, at least for today, in terms of the matching part. So with that, let's actually go ahead and move on to talk now about essentially offset cancellation. Now, I should mention here that although I've sort of called everything here to be offset cancellation, specifically in the context of this year's project, pretty much everything that I'm saying here, at least in let's say the second half of the lecture, in the second half of this particular set of slides, is just as applicable to not just canceling an offset, but actually to intentionally creating an offset, for example, to allow your 4PAM receiver to actually work the way it's intended to. Okay? So as I said, the sort of main flow of the lecture notes here will really be talking about how you just make things that have 0 offset, but many of the same ideas can be applied to actually get an intentional offset into your amplifiers or comparators as well. Okay, so for basically the rest of this lecture, we're going to talk about sort of 2 main ideas or approaches in terms of how you would get rid of offsets. In other words, how you would do offset cancellation. So the first idea, which will perhaps make more sense once we walk through the details, is to basically take that offset and somehow either modulate it or filter it so that it basically sits outside of the frequency band of your signals of interest. Okay? So as an example, if your signal is really sitting at DC, and of course your offset is also sitting at DC, the idea here is somehow I'm going to sort of do something to the configuration of my circuit so that the offset, instead of sitting at DC where the signal is going to land at some, let's say, higher frequency. Let's say a megahertz, 10 megahertz, 100 megahertz, whatever it is. Okay? So there's a couple of sort of different ways that we can implement that, and we'll see both of them in a second. One is so-called CDS, or correlated double sampling. This is sometimes also known as auto-zeroing, where the idea here is essentially on every single cycle, we'll try and measure that offset, store it effectively onto a capacitor somewhere, and then in the next phase actually put the signal in a way that subtracts off that offset. And the other actually sort of somewhat similar idea is the so-called chopping, where we pretty much literally try and modulate the offset to a different frequency band. Okay? We'll see that although the description I gave for these two is somewhat different, in principle they actually have many of the same effects in terms of, let's say, the frequency spectrum on the shape of the frequency spectrum in terms of what the offset ends up looking like. Question? Or? Okay, so I'll explain some of these more later. This DM is what's called dynamic element matching. This is not exactly the same as chopping, so to speak. This is actually something that's typically more specifically related to building digital to analog or analog to digital converters that have sort of known zero offsets. But I'll explain that a little bit later on, or at least, if I forget, feel free to bug me again later on. Okay, so this is one kind of big class of how you get rid of offsets. The other big class is perhaps something that's sort of more obvious, but also has its own, let's say, intricacies associated with it. And that's basically to essentially inject a quote-unquote DC signal that just opposes the offset such that the net effect is zero. Okay? So there's a couple different ways you can imagine to do this. One I believe you talked about in one of the earlier lectures with Pierluigi, which is kind of, you can imagine basically building a feedback system that just measures the DC component of the output of your amplifier. And to the extent that that DC component contains only the offset, you could then feed it back to the input and get rid of that offset effect. Okay? Another one is the so-called trimming idea, where you essentially just take a one-time measurement, and then based upon that one-time measurement, go and again inject some DC signal into the input to try and get rid of the offset. As we'll see a little bit later on, this trimming idea is often sort of implemented in a digitally controlled way. We'll see why that is, and in fact that's especially true for comparators. Okay, and again, we'll see why that is in more detail later on once we sort of get to talking about the specific implementations there. Okay, so let's sort of first focus on this first category of offset cancellation tricks. And so again, the general idea here is very simple, which is somehow what we're going to do is we're going to take our original amplifier that has some offset, and in fact, as we'll see in a second, 1/f noise as well, and we're going to make it so that amplifier has some configuration or dynamic configuration inside of it that makes it treat the offset differently than it treats the signal itself. So as I mentioned a second ago, this correlated double sampling, the basic idea there is that you configure the amplifier so that the offset is effectively going to be, you're effectively going to be taking the derivative of some signal, or really of the offset. And if it is indeed an offset, meaning that it's static, if you take the derivative, of course, its effect should go to zero. Similarly with this chopping, as we said, we're really going to just be taking it, we're going to be modifying the amplifier so that the signal just effectively goes straight through the amplifier. But the offset actually gets pushed up to a higher frequency and then filtered out. Make sense to everybody here? Okay, so let's actually look at what this really means, let's say, in practice. So the first technique I'll talk about is the so-called correlated double sampling, and you'll see why it's called correlated double sampling perhaps in a second. And this specific version is the so-called output offset cancellation. So the idea here is pretty straightforward, and as usual, it's easiest to understand what's going on by sort of drawing the circuit in the two different phases. So in the first phase, the circuit is essentially configured like this. We're going to ground both inputs into the amplifier, but I'm just going to represent the fact that the amplifier has an offset with this voltage source at the input. So this is not to say that I'm actually applying a real input to the amplifier. I'm just saying I'm going to lump all of the offsets into that voltage source. And as hopefully should be obvious, it doesn't matter if I put that voltage source on the plus or negative terminal of the amplifier. At the end of the day, it's a statistical quantity anyways, right? So it doesn't really matter where you put it. So I'm going to configure the amplifier like this. And I'm going to have that capacitor at the output, and I'm going to tie the output to ground. Okay? So, in this first phase, and this is of course indicated on the slide, but just to make sure it's clear, what's the voltage that actually shows up across this capacitor? Yeah, it's just the gain times the offset. Nothing magic there. Okay, so now in the second phase, all we're going to do is connect the positive input to the real input. In other words, the input we're actually interested in amplifying. We'll, of course, still have the offset on that other terminal. But then we'll just let go of the other side of the capacitor. And we'll use that as our output voltage. Well, so if everything happens ideally here, initially, that voltage across the capacitor, in fact, actually, initially, or in fact, actually sort of across all time, the voltage across that capacitor should not change. Right? Because there's no path for current to flow. And so there's no way for you to actually change the voltage on that capacitor. Well, so what that means is that we will continue to store A times the offset across that capacitor. So now when I apply this input signal, the only sort of change that I'll see out here is that I'll add A times the input signal on this side of the cap. And because the voltage across the cap itself cannot change, that means that the output would also be A times the input signal. Yes?
Theoretically, there should be a path for current flow because the output of the amplifier should be really low.
So you said the output of the amplifier is low impedance. That's correct. There can be current flowing inside of the amplifier. But notice if this is really an open circuit, none of that current can actually flow through the capacitor. It would just be flowing through some internal path on the amplifier. Okay, so you said, wouldn't you typically have some kind of load at the output? That's absolutely correct. You'd have, in fact, let's say some capacitor out over here. And that would just mean that rather than you getting really A times the input voltage, instead you'd get some A times a capacitive divider of the input voltage. Oh, okay, so you said if you have a resistive load, if you put a resistive load there, it's much like with a switch cap circuit. It's not going to work the way we intended it to. Right? Because things are just going to leak away and etc. Okay. So notice this is pretty nice because all we really did here was essentially store the effect of an offset across that capacitor and then just made it so that the input signal sort of showed up as a change in voltage across that capacitor, or rather I should say as a change in voltage on one side of that capacitor. And as long as that capacitor was big relative to whatever sort of, let's say, capacitive loading was on the other side, that AV-in would just show up on the other side of the cap as well. Now hopefully this is maybe sort of more clear why it's called correlated double sampling, in the sense that, notice initially what I'm doing is sampling the offset across that capacitor, and then I'm just relying on that stored or maintained offset to be the same, so that it cancels out the effect of the offset in the next sort of part of the operation, which is when you're actually trying to measure the input signal itself. So this approach indeed has a lot of nice advantages to it, but there are some issues as well. So first of all, as I've indicated in the slide here, and as hopefully you can kind of see from things, remember anytime you sort of turn a switch off, there's lots of errors that can get injected, and we'll talk in a lot more detail about that perhaps later this evening or next week. But basically, anytime you turn a switch off, you can inject some glitches or essentially just some transient errors into the system. So what's nice here is that because this switch in particular is at the final output of the amplifier, any glitch that's caused by this is really, from an input referred sense, attenuated by the gain of the amplifier. So in other words, if turning this switch off always causes a fixed, let's say, 10 millivolt glitch, then the fact that I have a gain here, let's say a gain of 100 as an example, would mean that from an input referred standpoint, that glitch only has an impact of, let's say, about 100 microvolts or so. Okay, so that's indeed nice. However, having said that, there is something we need to be sort of careful about here. So notice the voltage I'm storing across this capacitor is the amplified offset. So let's just sort of walk through an example and think about what would happen. So let's say that this offset, let's say it's 10 millivolts. And let's say that that gain there is 100. So in that first phase, what is the voltage sitting at that output of the amplifier right there? Yeah, it's a volt. Okay, so now you guys tell me, why might that be bad? Why might that sort of screw you? Okay, so you said the gain won't be at 100 if it's at a rail. Well, if your power supply voltage is a volt, then indeed you're kind of done, right? The whole thing is clipped out. Because I can't swing any more than my power supply to begin with, or maybe differentially you can. But the point here really only being that because I'm really storing that amplified offset, essentially the signal swing I have left over to use is going to be decreased by that offset. So in other words, if I could have a peak-to-peak swing of, let's say, I don't know, a volt or a volt and a half, let's just call it a volt and a half, while still maintaining my certain gain spec, then now if my offset could be as large as 10 millivolts, I've basically lost 2/3 of the swing I could actually use in my amplifier. Because I've only got that 500 millivolts left to actually be able to move the output of the amplifier due to the real action of the input. So in other words, if you're really shooting for something with a fairly high gain, and the offsets aren't exceedingly small, this thing really typically runs into pretty substantial issues of just not having sufficient swing at the output once you've canceled the offset. Make sense to everybody? Or? Okay, so it turns out there's, let's say, another way you can do things that gets rid of this problem. So what do you guys think that's going to be? How do you think you might be able to sort of cancel the offset without having to eat into your output swing range? Yeah, exactly. You basically have to somehow, rather than storing the offset at the output, store it at the input. So let's indeed see how you might do that. So I'm just going to sort of draw this version of the offset cancellation, and again we'll see sort of in more detail how it works. So let's say I take my input signal. I'm going to have these switches here like this, and I'll just draw the whole thing with all the switches, and then again we'll sort of draw it in a couple of different phases to see what it's really actually doing. And I'll take my output from here. So, in the first phase of operation, the way this thing is going to be configured is like this. So I'm just going to ground the input and tie this amplifier into unity gain negative feedback. Or again, I'm just going to represent the offset voltage right over here. So, in this phase, what is that output voltage going to be? Relative to ground, sort of as I've defined it there. What's the output voltage going to be? How's the amplifier configured? Okay, you said it's going to be V offset. Now, maybe just to answer the second question, how did you get to it being V offset? Like, what's the configuration of the amplifier? Yeah, it's just a unity gain feedback. All right, so now to be absolutely accurate, just because it is somewhat of a subtle but important point, is the output going to be exactly V offset? And I'll give you guys a hint. So is the output exactly V offset or not? Okay, so what is it?
V offset times A.
There we go. It's V offset. Nope. If I can get my pen to come back. Hello. That's weird. Just a second. Sorry about that. Let me just get this back into a reasonable configuration. Okay, there we go. Okay, so as we said, the output during this phase will just be A over 1 plus A times the offset. So in other words, if I'm interested in the voltage across this capacitor, what is that equal to? Again, the way I've defined it. Yeah, it's just the same thing. It's just negative of that. Okay? So now in the second phase, which of course is when I'm actually going to try and amplify the input signal, I'll just connect V in again to that capacitor. You'll be connected to the negative input of the amplifier. And as with before, I'll still have that offset at the other side. And I'll measure the V out over there. So now, as this hopefully should be clear by this, as before, that capacitor there is effectively just storing, okay, as we said, it's not quite the offset, but let's pretend it's basically the offset. So if I'm storing the offset across this capacitor here, then the only thing that should show up at this input, in terms from a differential standpoint, is really just the input signal. Right? Because notice, if this is storing the sort of negative of the offset, then when I measure the signal over here, it'll be V in minus the offset plus the offset. That exactly will be our differential signal, which would mean, in principle at least, the offset would just be canceled out. And our output signal now would be only the amplified version of the input signal. So notice, unlike in the previous example, here I canceled the offset at the input. And so because of that, my swing at the output can basically cover its full range. Now, just to be 100%, let's say, accurate or clear, as we said before, you don't really get the full offset stored at the input. So if you walk through it, what your actual output voltage will be is just A times the input signal plus 1 over 1 plus A times the offset. And hopefully it should be pretty easy to see how that happens, because as we said, you don't actually get the full offset stored across the cap. You instead get only A over 1 plus A. So the difference between that and the actual offset is 1 over 1 plus A. Make sense to everybody here? So as I said, the advantage of doing this is that now I really can get the full swing at the output of my amplifier. I don't have to sort of budget for that offset effect. That said, however, there are some, let's say, not so good things from this particular type of topology. So what do you guys think? What are maybe some disadvantages from doing things this way? Your signal's going to rail the output. Well, I mean, okay, that's possible, but you know, that's sort of no different than any other amplifier, right?
You could think of a way where you have high gain for offset cancellation and then low gain for the signal.
Oh, I see. So you're saying you want high gain for offset cancellation and low gain for the signal. I see. So you're saying if I don't have a high gain, you know, if I didn't have really that high of a gain because I didn't need it for my signal, then I'm not going to have really good offset cancellation here. That's correct. We'll actually see a way of doing that a little bit later on.
Your AC coupling the input?
Ah, okay, great. So you said you're AC coupling the input. What's bad about that?
Well, you're trying to actually send DC type signal.
Ah, okay. So let's actually think about this carefully. Notice, so you said that because I'm AC coupling the input, if I really wanted a DC type of signal, I may not see it. But actually, this circuit is kind of clever. So notice, I'm doing this repeatedly every cycle. So even if the input was constant, notice that from the standpoint of this capacitor, every cycle this side would be changed from ground to whatever the input actually is. So in other words, this is an example of, because of me using a clock, or because of the way I'm sort of modulating the configuration of the circuit, even though this looks like an AC coupling capacitor, I'm essentially making the input intentionally go from 0 to some value in order to make sure it actually gets through that cap. So from that standpoint, this actually does work. You know, you actually can get a DC signal through this thing while still canceling the offset. Yes?
Something that might be hard if you actually want to use this amplifier feedback to figure out how you can connect it so you're not messing up with that.
Ah, okay. So you said it seems like it might be hard how you use this amplifier in feedback in terms of figuring out sort of how you would do that without messing up all kinds of other things. Let's come back to that in 1 second. There's another, let's say, a very specific scenario that I'll show you how we'll deal with. But you did bring up a good point related to feedback. So what's different about, for example, this configuration versus this one here? Specifically from a feedback standpoint. Okay, you do have feedback. Why might that be bad?
Stability.
Yeah, there we go. Stability, right? So notice, in this thing here, that amplifier you built has to be unity gain feedback stable. Right? Whereas this guy here, there's no feedback. I don't care. It doesn't have to be sort of stable. I can kind of do whatever I want. Now, okay, obviously you can't do whatever you want, but the point being, of course, here you're intentionally placing that amplifier into unity gain feedback. Whereas maybe in the rest of the operation of the circuit, you actually didn't care about feedback. You don't really want it. You don't need it to be stable. And so, as usual, you might have to pay some penalty to actually ensure it really is unity gain feedback stable, even though that may not be the way you intended to use it. Okay, so that's actually sort of the first disadvantage. Which again is that the amp has to be unity gain feedback stable. Okay, any other disadvantages you guys might see here? I'll give you guys a hint. It's in contrast to one of the advantages we mentioned on the previous slide. Okay, there you go. It's sensitive to switch errors. Now, why would that be? Well, notice this switch right here, if there's some glitch, some of that glitch will go back to this input side over here. So in other words, if there's a fixed 10 millivolts glitch that ends up on this input right here, sorry, no gain, right? It just shows up directly as an effect on your input. Okay, so that's indeed the sort of second disadvantage of this, which is you are sensitive to switch errors because there's no gain to really attenuate those errors. So you asked, do those errors integrate? If you've designed this amplifier here to really be, let's say, settling fast enough, then no, because once you turn it into the unity gain feedback, it'll try and settle out whatever the previous errors were. If you don't do that, then indeed it quote-unquote integrates in the sense of it'll last longer than one clock cycle. Okay, so there's one other thing which was related to the sort of AC coupling, which is not that we can't get DC signals through, but there is, let's say, an effect from doing it. And actually it turns out the previous one has that effect too. So, input of that amplifier, is it really sort of a perfect open circuit, or does it usually have something associated with it? Okay, there's some input resistance. Let's say we're in CMOS so that that's really, really high. There we go, input cap. Okay, so why is it bad to have some input cap there? Yeah, exactly. It's just going to attenuate our signal. Okay? So in other words, it's just going to attenuate that signal by whatever that capacitive divider is. Now, in this particular, let's say, configuration, that's actually a particularly bad effect. Okay, because notice in this phase right here, well, let me take a step back. So if you wanted to make sure that that attenuation was small, how big would you make this capacitor relative to that input cap? Just, let's pick a standard number. If you want to make an effect small, what's the kind of, ratio you typically need? Heard somebody say it. Yeah, 10 times. That's a good guess. Okay, so if I make this cap 10 times as big as that cap, notice when I'm in this phase here, now my amplifier actually has to drive that 10 times larger cap to settle out the offset every single cycle. Right? So that means that I may actually have to spend power again in this amplifier just to settle out that offset. Even though in principle, offset should be a DC thing, right? Really shouldn't have any sort of settling or other types of requirements. So again, this capacitive divider attenuating the input signal is a particularly, let's say, annoying trade-off in this type of design. So if this is clear, this will maybe get back to your earlier question about feedback, which is, well, okay, so this is all nice, but let's say indeed that I can't actually just sort of take my overall amplifier, in other words, take this block here that I've said is an A, and actually place it into unity gain feedback. Right, so as an example, let's say that we actually wanted to build a comparator or something like this, which was going to have multiple cascaded stages. And kind of intentionally, we know that the thing is not going to be stable if I tied the whole comparator into unity gain feedback. So what I'm showing you here is kind of a simple trick, or at least a simple concept, as to how you would actually build one of these multi-stage amplifiers and get it to actually cancel the offset of each stage individually, or rather to cancel the overall offset of the entire design, without having to build sort of a multi-stage unity gain feedback stable structure. So the idea here is actually pretty straightforward. And if you look at it, it's actually now no longer entirely clear whether you're doing input offset cancellation or output offset cancellation. Because if you sort of look at it here at the input, this first stage, that kind of looks like input offset cancellation. But for this second stage, you can almost think of this cap as being storing the output offset of the first stage. Now, turns out this particular structure that I've drawn here really is doing input offset cancellation. But the reason for that is actually somewhat, let's say, subtle. So the real reason for that is that let's think about sort of how we would like to operate this thing to actually get the best possible, let's say, error characteristics. So if I look at this first stage over here, before I actually look at the input, as we said before, when you turn this switch off, it'll tend to cause some kind of a glitch, right? Well, that glitch will, of course, show up at the input of that amplifier, and then cause this V1 right here to be amplified by that glitch. Or rather, V1 will contain the amplified version of that glitch. Well, if my S2 is still on during that time, then what will happen is I'll actually store not just the offset of this amplifier, but the offset and the effect of the glitch onto this C2 here. So now when I turn off S2, of course, same thing will happen. I'll put a glitch onto this input. But again, if that next switch is still on, I'll actually be storing that glitch onto the next capacitor. So in other words, I'm really going to intentionally set this whole thing up so that I basically turn these switches off one at a time, just to make sure that I don't have essentially this very first glitch amplified through the entire chain of basically stages there. In other words, by doing it in this way, I can essentially successively cancel the glitches or the errors from each of those switches in each of the successive stages. Yes?
It seems like the glitches they don't have a way of canceling. It seems like even if you turn off the switches, you'll see the glitch on the cap and then they'll just propagate through.
But so here's the beauty. So if you think about, well, yeah, let's actually just show it here. So let's think about this very first stage. So, oops, that's white. There we go. If this switch here is still on, when the glitch happens here, that V1, instead of being equal to something like A over 1 plus A times V offset, now it'll be that plus some glitch voltage. Okay? So just for a second, this is somewhat of a recursive argument, but bear with me. Let's assume this S2, when it turns off, from whatever reason, doesn't cause any glitches. So if when this turns off, nothing gets messed up, this is the voltage I would actually store across this capacitor. Okay? Well, if I've stored that voltage across this capacitor, now, when I change this input over here, and it goes through the gain, right? If this glitch was still sitting around, and it doesn't actually have any difference between when the input signal is there or not, I've canceled it out. Right? In other words, you can't tell the difference between this glitch and the offset, because both of them are just stored across this cap and effectively canceled by the structure.
So the glitch is the same.
Exactly. So what I mean by this glitch is really that from whatever reason, as an example, when you turn the switch off, some charge got dumped into this capacitor right here.
So
And it basically,
it's like a deterministic.
Exactly. This would be like a deterministic or let's say systematic kind of error where every time you turn that switch off, some charge gets dumped onto the input and causes an error at the output. Again, as long as that thing is essentially, as long as it doesn't, let's say, change between the first phase of operation and the second phase of operation, it looks exactly like offset, right? It'll just get canceled out in exactly the same way. Does this make sense to everybody? Or? So again, just to be clear, the number one place where something like this is used is essentially these continuous time comparators, where you have a large number of amplifier stages, and you really don't want to have to tie the whole thing into unigain negative feedback to cancel its offsets. Instead, what you do is you essentially have each individual stage, or perhaps even sometimes groups of stages, cancel their own offsets, and then do this sort of sequential turning off trick, or let's say phase flipping trick, just to sort of mitigate all of those switch-induced errors. So, unless there's any questions on that, there's one point which is, let's say, a little bit subtle that I want to walk through and make sure it's clear. So as I mentioned before, this whole idea is generally known as either auto-zeroing or correlated double sampling. Now, if you think about it, offset in many ways is a lot like 1 over F noise, in the sense that it's basically concentrated at low frequencies. So what I want to do now is walk through and think a little bit about what would actually sort of doing this type of auto-zeroing or correlated double sampling do not only to the offset, but to 1 over F noise as well. So what I've drawn here is sort of, let's say, a conceptual or linear systems type of block diagram that in some senses at least represents the sort of exact operations we were doing with our earlier correlated double sampling amplifiers. So the idea here is pretty straightforward. So let's say we had some 1 over F noise in our amplifier. Right? Well, during the first phase, we have no input into the amplifier. There's just this 1 over F. And then what we basically do is we just sample whatever is coming out of the amplifier. Okay? And so just to be totally clear, usually this summation thing over here, which, by the way, this is kind of what the capacitor is doing, right? It's sort of storing an initial voltage and then looking for the difference between that and the future input. What we're basically doing is initially, during, let's say, the first phase of operation, we just store whatever the instantaneous input or offset voltage was. Then when we get into the next phase of operation, that's what this S2 is indicating here, then we actually feed in the input, and we look at the difference between that input and whatever voltage we had stored, let's say, half a cycle ago. So if I'm building this block that kind of looks like this, where I sort of sample a voltage and then look at the difference between that voltage and the voltage again at some period of time later. If you were to kind of, let's say, close your eyes a little bit and wave your hands, roughly speaking, what does that kind of approximate into from, let's say, a mathematical standpoint or from, let's say, a calculus standpoint? What kind of operation are you sort of doing? Yeah, it's basically a differentiation, right? Because if this sort of delta t became infinitesimally small, meaning 0, then you're literally taking the derivative. Well, here it's not that we're actually taking the exact derivative. Instead, we're taking the difference between a signal, or really in this case even a noise, and the same noise some period of time later. So to mathematically kind of, let's say, represent this or understand what the impact of this will be, I'm just writing out sort of a simple, let's say, linear model for this whole thing. So the idea here, again, is fairly straightforward. What I'm saying is that the output voltage at some point in time, and so, by the way, just to be clear, T here is the clock period. In other words, that's how often we're doing this correlated double sampling or auto-zeroing operation. K is like the sample number, meaning how many of these clock periods have gone by. And A is, of course, just the gain of the amplifier. Okay, so what I'm basically saying is that if I looked at the output at some particular clock cycle, kt, that's just going to be equal to the gain times the input signal at that same time, plus the 1 over F noise at that instant in time, minus the 1 over F noise 1 half cycle ago. Because if you sort of look at these waveforms, I'm assuming that you basically stopped sampling the 1 over F noise a half cycle before you actually basically look at the final output. Okay, so this would be sort of my, let's say, linear system model for what the output of this amplifier would be. Well, I'm going to abuse sort of notation slightly here, but if I took the Laplace transform of this output here, and I specifically am interested in what's the transfer function I'm applying to that 1 over f noise, well, remember, a delayed version of the same signal is just e to the minus s td, where td is whatever that delay is. So if I'm interested in the transfer function that I'm applying, or the filter that I'm applying to this 1 over f, notice it's basically just whatever, the output is just whatever the 1 over f noise is, times 1 minus e to the minus s t over 2. Okay, in other words, the transfer function is 1 minus e to the minus s t over 2. So, let's take a look at what that actually does in terms of a frequency response. So, there's kind of a few lines of math here, although actually, to be honest, there's nothing very sophisticated. I just first translated e to the minus st into its equivalent j omega form. And then from there, just as a reminder, e to the minus j omega times something is equivalent to cos of that something, basically minus j sine of that something. Okay? So once you have that, you can then, of course, just take the magnitude. Again, there's a little bit of, let's say, algebra here, but really nothing too complicated. At the end of the day, what you see is that the magnitude of that transfer function, interestingly enough, looks like a sinusoid. So let's just plot that to see why in the world something like that might be true. So again, let's look at the magnitude of this filter that's applied to the 1 over f noise versus frequency. As I said a second ago, it's basically a sinusoid-looking kind of thing. So in other words, it's going to look something like this. Okay? Now, just to be clear, at 0 frequency, what's the magnitude of the filter? Yeah, it's 0. All right. Now, given sort of the expression that I'm showing you here, hopefully it should also be clear that this peak magnitude here is 2. Now let's see if we can figure out why both of those are true, sort of from a purely intuitive standpoint. So first, if I put in a DC signal, as we said before, what we're kind of approximating is a derivative. Right? So in other words, if I have like this 1 over f noise that's constant, meaning it's the same over all time, if I just sample it once and then subtract that same thing later, of course it goes to 0. So by the way, from a frequency domain standpoint, the way to kind of see that this is approximating a derivative is initially the slope of that sinusoidal thing is exactly proportional to f. In other words, it's just like a multiplying by s. Okay? Now, given the same exact description, you guys tell me, why is the peak value here actually 2? In other words, why is it we're actually getting some quote-unquote gain off of the 1 over f noise at some frequency?
You sample, if your noise is at that peak frequency, then you sample it in one sine, and then by the next sample it's reversing the sine.
Yeah, exactly. This is kind of the equivalent of doing quote-unquote constructive interference, right? So if your noise just so happens to be at the wrong frequency, then when you sampled it once and then you waited that half clock period later, if its phase exactly flipped over, then now instead of actually subtracting two things that are kind of the same, now you're actually adding them together. So in other words, you could actually double the magnitude of the noise rather than canceling it out. So by the way, this magic frequency, what is that relative to your sort of operating rate? Yeah, exactly. It's exactly at Fs. All right, because if because like we said, you're sort of subtracting things half a period apart. Well, if the signal also has that same half period, it means it's at the same frequency as your clock. Okay? Does this make sense to everybody, or?
Would that hurt your clock speed? Like if you had some capacitive coupling in your signal?
Okay, so that's an interesting question. So you asked, would this sort of hurt your clock feed through if you added some capacitive coupling onto the signal line? So yes and no, right? The trick there is just that, indeed, if you really were coupling sort of your clock signal onto there, then indeed what you'd see is that you would basically be amplifying that clock signal up. Now, the thing we have to be a little bit careful of is, and this is where I abused notation a little bit, so I'm glad you asked the question. Notice here, everything I did was purely in continuous time. Right? Meaning, I did a Laplace transform on a continuous time thing, but in reality, I was doing discrete samples of these. Right? So now, if I'm going to then take this continuous time, let's say filtered spectrum, and sample it at fs, where is this effect going to land? Actually, is it going to land at a null, or like, in the sampled frequency space, where does it land? Like which frequency? So I have something that's at fs in the continuous time, and I'm sampling it at fs. Where does that land? Yeah, it lands at DC. Okay, so notice what's interesting about this is that indeed, if you were to sample some clock signal repetitively onto this input here, the sort of effect of that signal would indeed be amplified by a factor of 2. However, if you looked at the sampled output over here, what it would show up as is a DC error. Okay, so in other words, I would be canceling the offset, or the 1 over f noise, or at least the low frequency 1 over f noise of this amplifier. Right? That I would be basically getting rid of, because that would sit inside of that sort of signal band. But if there was some clock coupling onto the input, it would show up as a DC offset at the output. So in other words, I'm sort of trading whatever the intrinsic offset was for this sort of, let's say, I don't know, systematic or otherwise, coupling error coming from the clock getting onto the input. Does that make sense to people, or yeah?
Wondering about this. You're saying if you sample at the frequency that you're getting into, it seems like if you sampled it was the frequency or half the frequency you were getting into, because you're looking at the opposite phase, I guess. So I'm not sure why it's.
Oh no, so the only thing that's tricky here is that I'm doing this sample and hold not at fs, but at half, at half of the period. That's why that's happening. Yeah, that's a good question. Now, you did bring up another interesting point, which is notice, of course, if I was sitting right here, now it's as if everything is perfect again in terms of the cancellation, right? Because the phase just so happens to line up so that they're again perfectly in phase, and when you subtract the two out, the things are gone. Okay? So the real take-home message is that if you then look at applying this filter to the actual 1 over f noise of the amplifier, in fact, to the actual overall noise of the amplifier, then what we're doing is, of course, applying that filter to all of the noise spectrum first, and then we're going to be sampling it. So I apologize, it's perhaps a little bit hard to see, but I'll maybe sort of fill it in a little bit here. If you looked at, for example, let me get the pen. If you looked at, for example, what would the shape look like with a 1 over f noise, sort of sent through this filter, what you'll notice is that, indeed, down at DC, down at low frequencies, I'm really effectively getting rid of the 1 over f noise. Right? I've actually made it go all the way to 0. So you guys remember, way back when I said that 1 over f noise usually was not going to bother us because we were doing broadband stuff, but if you were really in an application that you actually cared about it, there's some tricks we can use to get rid of it. Well, this is one of those tricks. Okay? Now, that's not to say that it's perfect, but indeed, down at this low frequency over here, I've really substantially attenuated it. Now, of course, the bad news is that up at these higher frequencies, or in fact, let's say even at fs, I'm actually going to be amplifying relative to what it used to be. So now you guys tell me, given that this is the case, and given that as I sort of move my sampling frequency around, I'm going to push this point where I'm actually amplifying things to an even higher frequency, what does this kind of tell you about how fast you want to be running your, let's say, correlated double sampling? How would you sort of decide what's a good rate to be doing that? Say that again? Double the rate. Okay. Well, when you say double the rate of what? Oh, I see. You said double the rate of the sort of actual sampling you care about. That's one idea. Let's assume that at the end I didn't really actually want a sampled system per se. In other words, the only reason I'm doing this is because I want to get rid of 1 over f noise. So what's going to be sort of the trade-off? Or rather, which direction do you tend to want to push things? Just as a reminder, is the only noise coming out of your amplifier 1 over f noise? Or is there other kind of noise too? What other noise comes out of the amplifier? Yeah, thermal noise. So in the frequency domain, what's the sort of shape of that thermal noise before it's been filtered? Yeah, it's just flat, right? It's white, largely speaking. Well, if I take white noise and I pass it through this sinusoidal thing, notice I'm periodically going to actually amplify that thing up, right? So granted, there's certain places where I'm going to reduce it, but in general, amplifying it sort of outweighs the benefit of reducing it at other frequencies. Okay? So from a thermal noise standpoint, is this sort of a good or a bad thing to do? It's bad, right? So in other words, if I run this chopping sort of, by doing this chopping, I'm actually going to be amplifying more of the thermal noise. In fact, if I do it sort of at a higher frequency, I'm going to amplify even more of the sort of high frequency noise in terms of the thermal noise. But notice if I think about the 1 over f noise, right, from the standpoint of the 1 over f noise, which now let's actually sort of complete the plot here, right? If this is my 1 over f noise, there's going to be kind of this corner frequency, right? That corner frequency kind of tells you at which point in the frequency is it that you're more dominated by that 1 over f noise as opposed to by the thermal noise? So now you guys tell me, where do you think you want to run your chopping? Like what's sort of, what's a good point to be relative to? Yeah, the corner. Right? Because again, if you make your chopping too slow compared to that corner frequency, then notice I'll still be picking up a lot of this 1 over f noise by the time I'm actually starting to amplify it, right? Whereas if, as an example, and I'll just draw this in a slightly different color, let's say I actually ran my chopper at a higher frequency, how would that sort of change this sinusoidal picture here? Like, do the lobes get wider or narrower? So just a reminder, what is this point here? Yeah, exactly. That's Fs, right? So if I, for example, just to make up a number, if I triple Fs, then now this whole picture would, and let me try and do that a little bit better, would basically look like this, right? So from the standpoint of 1 over f noise, that's good, right? Because notice for this, down at these frequencies, I'm attenuating more of that 1 over f noise. Now, unfortunately for thermal noise, you're actually amplifying it, okay? So that's indeed exactly why you would want to choose this chopping frequency based upon what the actual 1 over f noise corner is. Right? Because if you choose it to be too low, you won't really get rid of enough of the 1 over f noise. But if you choose it to be too high, you'll just be amplifying more and more of the thermal noise. Okay, so there's obviously some, let's say magic numbers you can come up with. They're actually not too critical. The more important point is really to realize that there's this trade-off between how fast you want to do the chopping, because on one hand you want to do it fast to get rid of the 1 over f noise, but on the other you will actually pick up more thermal noise. And in particular, even though this thermal noise would actually be sort of, anything that's, let's say, beyond Fs over 2, right? Even though, it's beyond Fs over 2, so it will actually sort of fold back and show up in your sampled output. Does this make sense to everybody, or? Okay, so if that makes sense, let's just sort of briefly walk through the other approach for canceling offsets. Or the other, let's say, frequency domain approach for canceling offsets. So the idea here is somewhat similar, but in terms of, let's say, the specific details is a little bit different. So let me just sort of draw what this looks like, and then we'll walk through exactly how it's working. So let's say I take my input signal, and I feed it to this mixer, where the idea of the mixer is I'm just going to multiply the input signal by some periodic waveform. In this case, just a square wave of plus and minus ones. So now let's say that I have my amplifier there. And then that amplifier has some either 1 over F or offset noise inside of it. Okay, and then I have my actual amplifier. And then on the other side, I'm going to again multiply the signal by the exact same clock waveform. So the exact same sequence of plus and minus ones. I'm then going to take this output, let me just call that VO. I'm going to pass it through a low-pass filter and feed it to the output. Now, the best way to sort of understand, and let me just call this signal over here V mid. So the best way to understand how this thing is sort of working is perhaps to draw the overall picture in the frequency domain at each of these points along the amplifier. But before I do that, maybe it is worth mentioning the whole point of this thing is that from the standpoint of going from the input to the output, even though I've multiplied it by these funky things in the middle, if I multiplied it by essentially the same thing twice, and those sequences are such that when you multiply by each other, you just get 1, then notice from the input signal standpoint, nothing really should have happened, other than just that I got some gain, right? Because as an example, if I took the exact same sequence of minus 1 and plus 1, and I took any signal, I multiplied it by that twice, well, hey, minus 1 times minus 1 is 1. And of course, 1 times 1 is 1. Right? So in other words, I'm not really trying to do anything to the signal. But as we'll see in 1 second, from the standpoint of the 1 over F noise, something different actually does happen. Okay, so let's just walk through how that would happen. Okay, so let's say that this is, if we plotted the spectrum of our input versus frequency, let's just say it's some band-limited signal. So it looks something like this. All right, so now let's assume that sequence that I was multiplying by, just to make my life a little bit easy, and let me, by the way, call this V mid. Let's assume that rather than multiplying by a square wave, I actually multiplied by a pure sinusoid at some given frequency. So now, in terms of the input signal, where would that place the sort of spectrum of the input signal? Yeah, exactly. So if this frequency here was some F chop, then now instead of having sort of a DC signal, you'd have something that would be centered around F chop. Well, okay, as this hopefully should be clear from the diagram, I, for better or for worse, don't just have that F chop, or rather, just that signal, but now I've also got the noise from the amplifier. Right? And that noise, as usual, has some 1 over F region, plus some thermal noise dominated region, or some broadband region. Okay, so that's what that blue thing that I drew there is. So now let's think about what happens after I've gone through the second chopper. So that's going to be the spectrum at that VO right here. So, I'm assuming that these chopping things are purely sinusoidal signals, just so that I don't have to worry about harmonics of this other thing and draw those. For now, let's assume the amplifier itself has no frequency response. We'll come back to that in 1 second. That's a very good point, and we'll come back to it. Okay, so if I looked at this V out spectrum, well, as we said before, from the standpoint of the signal, nothing should have happened, right? I should have basically just gone back to DC. But now, how about from the standpoint of the noise? What does that end up looking like? Or where is that placed? Yeah, it's sort of shifted up, right? Now it's centered around F chop. So if I draw that, it'll look something sort of like this. Okay, notice I didn't sort of, end the peak there because it is 1 over F noise, so technically exactly at F chop it should go off to infinity. Okay? But now, hopefully, the reason why this is an interesting idea is clear. Because if I then take this thing and just pass it through my low-pass filter, well, if I choose my low-pass filter bandwidth appropriately, of course, my signal will make it through, but my noise, even though it sort of shoots up over here, if I have a good enough low-pass filter, my noise would actually just be attenuated. Right? Or in other words, would be filtered out.
By good enough, you mean with infinite attenuation?
I don't necessarily mean infinite attenuation. It's really more a question of how fast does the filter roll off as compared to the increase of the 1 over f noise. Right? So as long as the filter rolls off faster than the increase of the 1 over f noise, then basically you won't get a shape that is flat or continuing. It'll actually roll off like this. I don't know, but it's 1 over f. So if my filter is yeah, it's. That's right. But then the question is my filter? How fast is my filter rolling off, sort of at that point? So you're right. There may indeed be sort of like, how should I say this? There may indeed be some. There's always going to be some residual noise in that region, but obviously the faster my filter rolls off, the more I'll attenuate that noise. That's really what it comes down to, right? So I'm not saying that this makes it go to 0. But basically, you can actually substantially attenuate it. Right? Because even if I have a region that has, let's say, a delta at 0 frequency, remember, it's the area under the curve that matters. You see what I mean? Or
It still seems like you'd have infinite spot noise.
so if you were looking right at f-chop, then yes. But remember, the whole point of doing this is I don't actually care about f-chop. I care about a signal down over here. Right? So I can apply all kinds of filtering and try and knock that off. In fact, I can apply a notch filter exactly at that would have the same sort of infinite roll-off as the 1 over f noise would have had. In other words, imagine I just put a sync filter right here, exactly at f-chop. Then I would have no remaining noise exactly at that frequency. Okay? And if you're interested, we can do the math on the board later. Trust me, it does indeed actually work. There's a reason why people do this. Okay, so as we said before, this is like exactly in the category of taking the signal and basically somehow manipulating the signal so that it shows up at a different frequency band as where most of your noise is. Right, so if indeed you are really dominated by this 1 over f noise, rather than putting the signal on that same band, now we've moved the signal up at this point, and then what we've sort of cleverly done is move the signal back to where we actually cared about it, but moved the noise out somewhere else where we don't care about it, or we can basically get rid of it. Now, having said that, it's not that this is free. So, what's one thing we have to pay for to actually make this work the way we intended to? Yeah, exactly. So now your amplifier, let's say that before, this thing was only, as an example, 1 kilohertz, right? And let's say that my f-chop was now, 10 megahertz. Well, now I have to have an amplifier that instead of working at 1 kilohertz, actually works all the way up to 10 megahertz. Right? And by the way, typically when you do this, particularly because building sort of tuned amplifiers down at 10 megahertz tends to be huge, that basically means your amplifier just has to be broadband enough that it'll actually pass the signals up at 10 megahertz without basically screwing them up. Right? Whereas before, all you would have had to deal with is 1 kilohertz signals. Now, having said that, this is again still a very popular technique because it turns out that it gets to be very, very expensive to try and just kill that 1 over f noise down at that very low frequency. In fact, so expensive that you would prefer to just operate the amplifier at a higher frequency, pay that extra power for that, but not pay the extra power it would have taken you to actually knock this 1 over f noise down sufficiently down at the low frequency. Does this make sense to everybody? Or? Okay. So the question was, do you pick up a lot of extra thermal noise? So now you guys tell me, how do you sort of arrange things so that you don't pick up a lot of extra thermal noise? That's an excellent question, by the way. So what's the sort of extra knob I can play with to try and make sure that I don't actually end up picking up a lot of extra thermal noise? Yeah, exactly. The filter bandwidth at the end, right? Because, and by the way, this is now I've really sort of been a little bit, let's say, fast and loose. Let's for now assume these really are perfect sinusoids, right? So that all I'm doing is just frequency translation back and forth and not with additional harmonics. Then, indeed, whatever thermal noise was in this amplifier, all I did was just translated it up to a higher frequency, right? Well, hey, if I'm just going to filter it out by whatever bandwidth I would have had through, if I just imagine this whole thing was just some composite amplifier with this same bandwidth, then really I haven't done anything, right? Because taking something that's flat and moving it to a higher frequency and then just filtering it doesn't really matter, right?
Well, I'm actually not really filtering it at the frequency of your signal, though.
Not really filtering it. Well, so I guess what I'm basically sort of getting at here is that notice the noise here. Right? If I looked at it in terms of what's still sitting in my signal band, all I've really done is take particularly the white part. All I've really done is taken something that used to sit, let's say, down, I don't know, at DC or even at negative frequency, and made it sit at where my signal frequency is now. But at the end of the day, if the spectral density is the same, why do I care whether the noise originally was from here or from there?
Right, I guess I'm wondering if you have maybe if triggering pulse noise, but it seems like if you have this really wideband amplifier, you could potentially be adding more noise just due to that amplifier, which is just increase the magnitude.
Right. Okay. So here's your point is a very good one, but there's a little bit of a subtlety there. So what you were both saying was that, hey, look, if this is a really wideband amplifier, if I looked at the voltage magnitude of noise here, in other words, I just sampled the noise right at this V mid, you're both absolutely correct. It would be larger than what you would have gotten from an equivalent amplifier with a narrow bandwidth. However, the point I'm making is that I don't actually care about anything here. The only thing I care about is after this filter. And after the filter, if I make the filter bandwidth the same as the bandwidth I would have had from the equivalent, narrow band baseband amplifier, meaning without having done this chopping, I would have the exact same noise. Because all I'd be doing is getting rid of all of the extra high frequency content that was being inserted by that amplifier there. Right, so in other words, the thing you have to remember is you can't just treat noise in absolute magnitudes. You always have to keep track of the spectrum. Right? So if you integrated it here, you're absolutely right, you'd get a larger answer. But the trick is I'm not going to integrate it there. I'm actually going to filter it first and then integrate it. And that's why this doesn't actually cost you anything from that, or at least intrinsically it doesn't have to cost you anything from that standpoint.
If you multiply by perfect.
Yeah, okay, exactly. So now you're laughing. As I said, I'm multiplying by perfect sinusoids. I'm being a little bit fast and loose with that. But the good news is you can do a pretty good, even if you're multiplying by square waves, you can still actually do a pretty darn good job of that, simply because usually you're talking about very, very low frequencies here. And so even the additional sort of folding and et cetera you pick up usually is not too bad. In fact, there's even other tricks you can play with these mixers to make it even approximate a sinusoid very, very nicely. Now, having said all that, what does get to be a little bit tricky is that much like with a correlated double sampling, these mixers here usually are implemented out of some kind of switches. And unfortunately, when you turn those switches on and off, you get some kind of glitches happening at the input. And so you can imagine if I have a glitch that's here at this frequency and at the same frequency over there, like we had said before, it can translate then into some DC kind of error. Because you sort of create the glitch at F and then sample it at F, and it again lands back in your signal band. Okay? And as you might also expect, the faster you run these chopping switches, sort of the larger the glitches you're going to get. So it turns out that one sort of very common trick is to not actually apply this chopping trick just once, but actually to apply it even twice. Okay? So this is very similar to the sort of correlated double sampling we had looked at before, where the idea is the following. So you tend to want to run this chopper at a relatively high frequency, just because the higher the frequency is, the farther away you push that 1 over F noise. Right? And then the easier it is to actually filter it out. But as I said a second ago, if I looked at the errors due to those sort of switches or those mixers, higher frequencies tend to actually cause more of those errors. So the idea here is sort of an interesting one. What they basically say is, well, let's build one of these so-called chopper stabilized amplifiers and run this one at a relatively high frequency, exactly to get rid of this 1 over F noise. But now, because I know that that's going to cause some additional residual errors due to the switching of these devices, and by the way, this thing here is just what's known as a butterfly switch. It's basically just a way of either passing the differential signal through or flipping its sign. So these two things, you can just, again, think of them as being mixers. It's just that it's with plus minus one instead of with sinusoids. So the idea here is I'll take my first sort of chopper amplifier, and then I'll chop it one more time. With the idea being that what I'm trying to do with these extra choppers here is just get rid of the additional sort of spiking or glitching errors caused by this high frequency chopper inside of here. And because these now can run at a lower frequency, because they're only trying to get rid of those, let's say, second order types of errors, you can make the glitching errors of this external chopper smaller than the glitching errors of this internal chopper. So again, the idea here is this so-called nested chopper amplifier, where you're not only trying to get rid of the 1 over f noise of the amplifier itself, but you're going to use the same idea one more time to actually get rid of the errors caused by the high frequency choppers in the first place. Okay, now as you can imagine, you can sort of go nuts with this. You can start doing, nested choppers and etc. But this particular configuration of so-called, doing the nesting at least once is indeed quite common. And so that's why I wanted to mention it here, because if you look in the literature, you'll see this in quite a few different places or in many different applications. Does this make sense to everybody? Or? So, unless there's no further questions on that, let's just maybe briefly start. Oh, yes?
So when does this flicker noise start becoming a problem? Like, for example, in a project, we've been calculating it, and then at the end our noise was within 10% of what we thought would. So these are all very nice techniques to get rid of it.
Okay. So your question was a very appropriate one. So you said, well, hey, in our project, it seemed like flicker noise basically didn't really matter, right? Because you would calculate your noise just on thermal, and then you'd add in the flicker, and it didn't seem like it kind of did anything. Well, I was quote-unquote nice to you in this project in that I gave you a fairly broadband system, A, and B, I gave you a sort of, let's say, lower flicker noise corner, meaning a operating time that wasn't too excessively long. Right? So I think I said something like a kilohertz, which means you're only operating on an order of a millisecond or so. Right? Well, let's take a different application space. So as an example, let's say you wanted to do something like an accelerometer. Okay, well, in an accelerometer, the signals you're talking about are moving, let's say, if you're lucky, let's say at kilohertz kind of range. Right? Well, anybody actually happen to take a look? What was the 1 over f noise corner of your devices? Particularly the short channel devices for sort of reasonable V star and the kind of reasonable bias points you guys were operating at. A couple megahertz. Okay, in fact, actually, for modern technology, can easily be up in the hundreds of megahertz to not even actually gigahertz range. Okay? So if you're looking for a signal that's down at a kilohertz, and your 1 over f corner is at a couple megahertz, guess what? It's going to be all about 1 over f noise. Right? That's the only thing that's going to matter, almost. Right? Because your bandwidth is going to be so incredibly narrow that the thermal noise almost is sort of, yeah, it does matter. You have to be careful with it. But if you don't do anything, the 1 over f noise just completely kills you. Okay, so there's a big body of these sort of, let's say, sensor types of applications where everything is about essentially getting rid of these offsets and 1 over f noise type of effects. So it's a really good question. Other questions on this? Or? Okay, so it looks like we actually used up our time for quote-unquote today. As I said before, we'll be doing the makeup lecture at 5:30 this evening. And just as maybe to get more people to show up, that's where we'll actually cover the stuff you'll really be using in this project.